The last lecture we have discussed about half wave and full wave rectifiers, and we have seen that the output of a full wave rectifier contains a pulsating character. That means the output is not a constant voltage, it varies from 0 to the maximum peak input voltage Vm. So in between the 0 and maximum peak input voltage Vm, there is a variation of the output signal or output of the rectifier. So this pulsations has to be avoided. So we can say that output of a full wave rectifier has a pulsating character. This pulsation is actually due to the AC component present in the rectifier output. So it is not a pure DC, but it also contains the AC component. To understand how this AC component comes in the rectifier output, we just look into this diagram. This diagram actually contains the first part is a DC, the representation of a DC voltage with a plus 32 volt, and when it is added with a signal which is having a variation from minus 32 volt to 0, then 0 to plus 18 volt, so it has a both positive and a negative part. So this is an AC signal. So this AC signal has a negative minus 32 to plus 18 volt variation. So it contains both positive and negative parts. So this is an AC signal. When this DC signal with the positive 32 volt and this AC signal is added, what we are getting a signal like this with a VM, the maximum voltage is 50 volt. This is the result of the addition of this DC and yes, this AC signal. So we are getting an output like this or voltage like this. This voltage is exactly resembles to the rectifier output of the signal. So we can say that a rectifier output voltage actually contains both AC and DC component. So this DC component, we need this DC component in to the load, and the AC component has to be eliminated. So these variations or the pulsations in the rectifier output is otherwise called the ripples, and these ripples, the measure of the ripples is actually the measure of AC component in the rectifier output. And for effective rectification we should reduce these ripples or AC component in the circuit. So the measure of this AC component in the rectifier output is represented by a quantity called a ripple factor. The ripple factor is defined as the ratio of the RMS value of AC component in the rectifier output to the value of DC component in the rectifier output. So from this equation, this ripple factor is given by RMS value of AC component in the rectifier output divided by the value of the DC component. So we can represent it like this: VAC by VDC. It is same as representing IAC by IDC. So the ripple factor is given by VAC by VDC or IAC by IDC. If the rectifier circuit is more effective, means that the AC contained in the circuit is lesser. So if the AC component is lesser, then ripple factor will be less or smaller. So we can say that smaller the ripple factor, lesser the effective AC component, and more effective is the rectifier. Now let's have a look into the mathematical analysis of this ripple factor. Suppose we are having an output signal, rectifier output, and which is having an IRMS value. That means IRMS represents the effective value of the load current. That is, by definition, we can express this IRMS as square root of IDC square plus IAC square. So from this equation, This equation can be rewritten in this form: IRMS square is equal to IDC square plus IAC square. From that we can write the expression for IAC as IAC is equal to IRMS square minus IDC square. Now we need the expression for ripple factor. Ripple factor is given by IAC divided by IDC. So divide this equation by IDC. Divide this equation by IDC. So IAC ripple factor is equal to IAC by IDC. So ID 1 by IDC into square root of IRMS square minus IDC square. Take this IDC into the square root, so it become IDC square. So what we are having is IRMS square divided by IDC square minus 1. So this is the expression for the ripple factor in terms of the current, that is RMS value of the current, and this RMS value, remember, that is the RMS value of the AC current, and IDC is the value of the DC current in the rectifier output. So this is the general expression. Now let's see what is the ripple factor for half wave rectifier and full wave rectifier separately. For that, first of all, consider the half-wave rectifier. Again, the base we are using the definition: ripple factor is equal to IAC by IDC, which is equal to square root of IRMS square divided by IDC square minus 1. Or in practical cases, we can directly measure it as VAC by or VRMS by VDC, where VAC is the AC component in the output voltage, and VDC is the output DC component in the output voltage. Generally this is the expression. And but for an half wave rectifier, we know the expression for IRMS as IRMS is equal to Im by 2, and IDC is equal to Im by pi. So if we substitute this IRMS and IDC in the above expression, we can see that our ripple factor is equal to Im by 2 divided by Im by pi all square minus 1, which is comes out to be, if you do this calculation numericals, you will find that this value is 1.21 for an half wave rectifier. And you can see that it is greater than 1 means this quantity is greater than 1. Ripple factor is greater than 1 means IAC is greater than IDC. So the AC component is greater than the DC component in the case of a half wave rectifier output. Now let's see what is the value for ripple factor in the case of a full wave rectifier. For a full wave rectifier, the IRMS is given by Im by root 2 and IDC is given by 2 Im by pi. Therefore, ripple factor is given by this equation. If you substitute the values of IRMS and IDC, you can see that this comes out to be 0.48 for a full wave rectifier. So for a full wave rectifier, 0.48 is the theoretical value of the ripple factor, and for a half wave rectifier, 1.21 is the value of the ripple factor. So remember that the lesser values of ripple factor means lesser will be, or smaller values of ripple factor means lesser will be the AC component in the rectifier output. If the AC component of the component in the rectifier output is lesser, then it means that the rectifier effectiveness is more. So more the rectifier is more effective. So when ripple factor is smaller, then effectiveness of the rectifier is greater. So that is the conclusion we can have, or we can obtain, conclude from the measurement of the ripple factor. So remember that measurement of a ripple factor actually represents the measurement of the effectiveness of a rectifier. Or in other words, we can say that the effectiveness of a ripple factor is expressed in terms of the ripple factor. And now we can see two problems here, and the hints are given here. So let's try to do these two problems for uh, getting an idea about the ripple factor of a circuit or a rectifier. Okay, thank you.